So good afternoon, Chem 227 students. So once again, welcome to Bioinorganic Chemistry. So for this afternoon, we're going to have an overview of what is bioinorganic is about. So allow me to share my screen. So now that it is shared, so let's proceed. So roughly saying, we're telling that bioinorganic chemistry is the role of metals in biological systems. So what is indeed this role of metals in the biological systems? So bioinorganic chemistry is actually at the interface of many disciplines. So you might have an intuitive guess about it based on its name. So bioinorganic. It actually involves, of course, the classical inorganic chemistry. So in here, we deal on the properties, reactivities of elements other than carbon and their compounds. Actually, we also include carbon in here, but in the sense that it is more of looking into inorganic compounds of carbon. And then we have the classical organic chemistry, which deals on the properties and reactivities of carbon and its compound. And as related to this, very closely, the biochemistry of these organic compounds. Along with this, we're also looking into the classical biology, which takes a look into the structure and functions of all forms of life. So that's why we refer to it as the role of chemistry, or rather of metals, to be specific, in biological systems. So bioinorganic chemistry, you might not realize it, but it is actually interrelated to several disciplines such as microbiology, physics, the toxicology, pharmacology, physiology, among others. Okay. So what we have actually is a very non-stringent coverage. Okay. And this is an exciting specialization with respect to inorganic chemistry. So bioinorganic chemistry is the study of inorganic elements in living systems, particularly looking into the role of, first and foremost, the metals in the structure and function. There are two major components, or when we say inorganic chemistry, what do we study? We have those that are naturally occurring inorganic elements in biology. And the second one, so the introduction of metals into biological systems, particularly as probes and drugs in its application in medicine. So which elements are we really talking about here? So the periodic table is huge, right? I think we have more than 110 elements now, including the synthetically prepared ones. But when we talk about bioinorganic chemistry, we sort of limited with those that can be categorized under either naturally occurring or can be introduced into biological systems. So I have a rough illustration of which elements are important in bioinorganic chemistry. So those colored red are the ones that are naturally occurring. So it expanded even from the main group. We have sodium, magnesium, potassium, calcium. And of course, we have it here in the transition metal, although zinc and cadmium are not considered transition metal, but rather in the D block site, we have most of it would be the first row, D block elements. And then we have some more interesting ones. Among the heavier ones, we have molybdenum and tungsten. The ones that are colored gray are the ones that have been used as probes or drugs. So specific applications in medicines. Although, take note, I got this from the Lippard book, and that was published in 1994. These applications in medicine actually has been expanded already, and some of them might include first row transition metals as well. So it is quite just a handful, or a very small number as compared to the totality of the number of elements there is, but the chemistry is quite abundant with respect to the following elements. So some examples, we have here the sodium-potassium pump, which are generally involved in the regulatory function. So these are ion pumps. And then we have particularly, say, calcium involved in structural roles. So present in our bone density. So a huge majority of what we have would be those that have catalytic properties or might be even involved in redox reactions or electron transfer, such as hemoglobin. And then we also have some metallocoenzymes, such as vitamin B12. And they are also involved in gene expressions, such as this zinc finger illustrated. And I hope you realize it that bioinorganic compounds are very much prevalent in biological cycles. So in this biological cycle, so in the bacteria, the conversions or the site that are quite important where the conversions occur. So these following conversions occur are in a metal-centered type of a site. So summarizing those up, or just giving an overview. So we have here the common biological functions of some of the elements, included in here as well as the non-metals. But nonetheless, so we can be involved in charge balance and electrolytic conductivity. So also structure or structural functions, some signaling functions. It can also be involved in catalysis, both Bronsted and Lewis acid-base catalysis. So electron transfer and group transfer are also the important functions of these biological or bioinorganic compounds. Also redox catalysis, particularly those that involves D metals or transition metals. And we have energy storage and biomineralizations to include in the list. So for this, we're actually going to focus on the essential elements for the living systems. So among those 110 or so elements, there are only a few considered to be essential elements. So this definition of being an essential element has been based on the work of Klaus Quartz in 1970s. And there are actually several criteria that can be considered for a certain element, okay, to be categorized as essential. First off, when we're going to look into its importance, so there will be a physiological deficiency if the element is removed from the diet. And this deficiency will be relieved if the element is included in the diet. And then lastly, the element should function specifically, okay, in the organism. So it has a certain biological function. So if you take a look into the criteria that is listed, it depends on really how the element is consumed by the organism and what is the specific function of that element in the organism. So we have, for human, 20 essential elements, and 10 of which would be metals, both main group metals and transition metals. And then we also have some non-metals. So among those, and quite in abundance with respect to, say, weight per weight in a human body, we have hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus. This constitutes about 98% by weight in a human body. This is because, well, these are the elements that are basically part of, say, proteins, nucleic acids, and so those are biopolymers that we have. So that's why it really takes up or make up a huge part in when we consider weight by weight. But along with this, so we're going to add up some more elements, particularly the following ions. So sodium plus, potassium plus, chloride, magnesium plus, calcium 2 plus. So those that are involved in structural and in signaling or ion pumps. So electrolytic functions. These make up 99% total. So only added up about 1.5% by weight. Okay. So the hydrogen, carbon, nitrogen, oxygen, sulfur can be considered as bulk elements because they are really present in huge amount. And then the following elements, sodium, potassium, chloride, magnesium, and calcium can be considered as macrominerals. And then we have the trace elements. Most of these are the D-blocks element, transition metals, so which includes manganese, iron, cobalt, copper, zinc, and molybdenum. And to make up for the 20 essential elements, we have these non-metals, which can be considered as ultra-trace elements. So their amount in the body are very low, but they are still quite important in terms of the biological functions that it has. So we have bromine, iodine, and selenium. So for these essential elements, actually, somewhat we can call them beneficial elements or beneficial metals. But the differentiation between toxic and beneficial sometimes depends on the concentration of the essential elements in the body. And we have this condition referred to as homeostasis, wherein, so simply put, we have a set of related and controlled steady states in processes involving continuous changes in material, charge, energy flows into, out of, and within cells. So those transfers into the cell, out of cell, and within the cell. And take note, not only matter. So you also need to have a balance of charges and the energy associated with this transfer. So that's why homeostasis is a state wherein essentially that should be kept, and this is kept wherein the concentration of the essential metals in the body is within the strict limits. So there is only a strict limits. So I found actually a cartoon here, a little bit funny for me. So describing or asking what homeostasis is really. It is the way that the body controls its systems. So we're talking about balance in everything. So matter, energy, charges. So maintenance of controlled levels of all the chemical components. So we can somewhat more visualize that if we take a look into this dose response curve for the essential elements, and this is for human. So we achieve homeostasis if that is within this optimal level. So this is the element, the x-axis is the element dosage. So how much is it, okay, in the body? And this would be the response associated with that dosage. So there is, as you can see, a certain amount, a certain limit that we can see over here. And if it is less than the optimal amount, so we have a deficiency, okay, although a little bit still surviving. So it will still, the organism will still survive, but that certain essential element is deficient in the body. But beyond the optimal amount, so we have toxicity, and eventually it becomes lethal. Okay? So all of those essential elements, essentially, there's only a strict limit that should be present in the body, and be less of it or beyond of it, that's an unfavorable circumstances. So the main questions that we should be asking now is, among those 110 or so elements in the periodic table, why just these elements in biological systems? Okay. First reason, of course, is, well, these are the elements that are quite abundant. So if you recall the abundance of the elements, of course, hydrogen is very abundant, but those that are listed are basically those that are abundant in the solar system, on the Earth's crust, or in the ocean, where there's a consensus that that's where the life started. Okay. So they are the ones that are quite abundant. So the organisms at this very early stages of life consume these elements or find importance to these elements. Okay. That's why these elements are the ones that have or that are essential. But some elements are quite abundant but are not essential, because we also need to consider its bioavailability. So bioavailability is how it is available for biological system, or how can it be readily assimilated by the biological systems. So these elements are easily assimilated by biological systems, or there are some mechanisms that the biological systems can perform so as these elements can be easily taken into the biological system. So they are indeed in the right place at the right time. And lastly, of course, these elements fulfill a certain function. Okay? Especially at the start or at the early stages of life, these elements are the ones that have a certain function while the organism is developing, and this function cannot be fulfilled or may not be fulfilled by other elements. Okay. Either other elements can be detrimental if these are substituted into the elements, or really the other element does not have the same function as these essential elements have. So just to have an overview again, so we have important considerations that these elements, when they are in biological systems or they make up a metal-centered compounds for biological systems, these compounds are kinetically labile and thermodynamically stable. So the lability facilitates the rapid assembly and disassembly of, say, the metal and the biological system interaction, or the rapid association and dissociation of substrates. So you might notice, especially for the transition metals, that the somewhat lighter ones, the first row, these are lighter ones. These are the ones that are important in bioinorganic systems. The heavier ones are actually not very much involved in biological systems. And in fact, they are toxic. they are considered to be toxic. That's why I think in your analytical chemistry, you are warned of these heavy metals because they are toxic. But take note, those heavy metals are actually the ones that are important, say, in organometallic systems. They are the ones that are functioning well as catalyst. So each has a certain function. And for bioinorganic systems, the lighter transition metals are the ones that are quite important. So these elements actually, their concentration, so there's a certain concentration, optimal concentration, and generally this concentration is maintained because it is energy driven in the cell. So to fulfill a certain or specific function in the cell, so the concentration is energy dependent. An increase in the concentration, a decrease in the concentration is associated with changes in the energy. And then, since they perform a specific function, local environment, okay, around this bioinorganic system attenuate the properties of the metal to optimize these specific functions, particularly, so in evolution, development of specific organic functionalities in these biological systems that can modulate the properties of the metal or the inorganic gas. So we have it here, a summary of how we can put that into play. So for example, sodium and potassium, their binding ability to biological systems or biological ligands are actually weak. Okay? Yeah. Well, they are really rare react metal ligand combinations. Except for water, they are very much easily hydrated. But their mobility is high. So that's why in the biological system, they function as charge carriers. So in contrast, so when you take a look into magnesium and calcium, their binding ability is moderate and they are only semi-mobile. So usually they function as structural or signaling. So for signaling, you just need to activate them so that it will move from one point to the other, but it does not really necessarily should always be mobile. And then zinc, we can see in here a moderate binding, intermediate mobility, but aside from that, we know that zinc is a very good Lewis acid. So Lewis acid catalysis, or it can also function as structural. But these transition metals, they have very strong binding ability. They have very low mobility. They can exhibit several oxidation states. That's why their chemistry is quite rich in terms of they can function as redox catalysts or oxygen transfer for oxygen chemistry. Okay, so I hope that settles why we're only looking into several elements and not all, because not all elements in the periodic table are important in the bioinorganic or in the biological systems. So moving on, most of what we know about these bioinorganic systems are actually brought upon by the progress and advancement in this analytical techniques that can be used to probe metal-containing systems. So we have a summary in here. So this can be done in solution, in model systems, or in living system. But what is important, so that we can get clear information about this bioinorganic system, is that you're working on with a pure sample, and that you would want to use advanced techniques to characterize these pure samples, and you're not limited to only one technique. In fact, a combination of the techniques is usually done because one information is complemented by the information provided by another technique. So here are some of the techniques. So this is not exhaustive, but these are the common techniques, I would say, that are usually used in probing bioinorganic systems. So we have X-ray, using X-ray, either diffraction or absorption. And we're also using the magnetic property of these bioinorganic systems, either looking into the nuclear magnetic property or electron. Okay? And then quite specific to ion, we have the Moss-Bauer. And then we also look into optical spectroscopy. So either the simple, well, relatively simpler UV-Vis, the electronic absorption, or in conjunction with this, we have circular dichroism or magnetic circular dichroism, which also can tell us something about the chirality. Then luminescence and infrared and resonance Raman. And not very much based on spectroscopy, but electrochemistry is also sometimes used, particularly for those that might involve changes in oxidation states. So majority of this analytical techniques actually manipulates the spectrochemical phenomena summarized in this figure. So we have matter, and interaction of matter with the electromagnetic spectrum can be, it can scatter it, it can absorb it as well, it can transmit it as well as refract it, and then reflect it or emit it. So in this slide, I'm showing you some of the properties that can be gathered when we look into the following techniques. So we have X-ray, absorption spectroscopy, okay, for UV-Vis. So these are the following electromagnetic region that are involved. So for example, for IR as well as resonance Raman. So we're taking a look into molecular vibration. So resonance Raman is a conjugated Raman spectroscopy wherein the you're taking a look into, you're exciting it to get the Raman spectrum at the wavelength where it has an absorption. So it makes it having a more intense resonance Raman peak. So we have EPR for electronic spin, and then NMR for nuclear spin, and so on. We will have examples of this as we go on with the course, depending on what is important with respect to how that bioinorganic system is analyzed. But with respect to the details of how the technique is done, what is the principle behind, my students from Chem 220 in the first semester of the academic year 2020-2021 actually prepared a presentation for this, which I will be sharing to you. And they also have some examples there, but the examples are limited to general inorganic systems, not necessarily bioinorganic or biological systems. But you will find use, or you will find these presentations useful. Okay, so that's it for our overview of the bioinorganic systems. We will have a more detailed discussion about this as we go on per chapter, starting chapter 2. So thank you very much, and have a nice rest of the day, and always keep safe.